Okay, I think that we are now ready to start. Uh, Thank you for being the second day with us. And today we will have a workshop for the blue energy planning in Croatia. Uh, we will start with Professor Goran Kracic, where he will tell us about the vision of sustainable Mediterranean islands and how to turn a vision into reality. Professor Kracic is the head of the Power Engineering and Energy Management Chair at the University of Zagreb, Faculty of Mechanical Engineering, and his main research area are on the sustainability and energy planning. So, Professor Kracic, the floor is yours.
Thank you, Hrvoje. Good morning, everyone. I hope that you see my presentation. I just want to confirmation from your side.
Everything okay? Is fine. Yeah, you can continue. Thank you.
Okay. So I hope you have a better weather in Split than we in Zagreb and in other places. But this is something that will change soon. My talk today will be how to change this vision of sustainable islands in reality, which is not so easy. We know that we have a lot of things in our strategies, in our plans. However, sustainable Mediterranean islands should be the ultimate goal, and we all strive to achieve them. So, first of all, I would like to say here that maybe to be sustainable, you need to be smart, and this is way how we should think, and this is something that Daphne network of sustainable Greek islands come out with through declaration of smart islands, which was product of their activity together with other islands in Europe. Here in just definition of smart island, which is quite close to the sustainable island, we can see that they covered all of important points, like we need to build our systems resilient to the climate change, but at the same time use these mitigation options to utilize more energy and to enhance local economical development while preserving a high quality life for the local population. This will be, I think this will happen through integration of smart solutions, which will also help to manage infrastructure, natural resources, and environment. So we know that ICT is and digitalization is coming, and that it is present in more and more things. So we think that this will also help and speed up process of building sustainable islands. And at the end, what is more important is to bring innovation to the islands and build a social inclusive governance and financial scheme. So this definition is quite long for English language, but everything is in it. And if you really work on this and set up this as a vision, I think your island or our islands are on a good way. So that's why this vision of smart island is integrated in declaration of smart islands, which is a bottom-up initiative. So the islanders, more than 300 islands came together in 2017 and in Brussels signed this declaration, by which they are trying to work on topics that I have said before. So in the same time, European Commission also had shared this vision of sustainable and clean energy for islands, and so there were two declarations, or let's say memorandums signed. The first one is on Malta Clean Energy for EU Islands, and then supported by last year's memorandum of Split, where this island secretary is enhanced, and the result of which we know that there is so many things around this secretariat, who is working now on energy transition of many islands in Europe and Mediterranean. So I hope you will be able to sign for the next forum on this clean energy for islands, which is going to happen tomorrow and day after. So you're welcome to join. The European Commission also set up the Responsible Island Prize, which should show which islands are the most advanced in this sustainability and responsibility towards the clean energy and the energy transition. And here we can see that certain points were evaluated in this award, and how they see what is important. So first of all, this is a share of renewable energy that you supply from your local resources, which means not imported by cable or any other means to the island. Then you need to work on sustainable issues like environmental and social sustainability of your solution, then involvement of citizens. So it's not enough to build just your facilities. They should be somehow integrated in local community and local ownership. And finally, they also evaluated replicability of solution, which means that other islands can follow you and then use your solution. So here we have just some kind of winners from 2019, this award prize, which I think are good showcases and islands which you can look at to see how they are managing this sustainability and how close they are to our sustainable development goals. So here we have island of Bornholm in the Baltic, and island of Samsø, Danish islands, and Orkney Islands. So you can see that all of these islands are from the northern seas, which means that maybe communities, people and governments and researchers there are really keen to go forward and are quite advanced. So maybe the time for them is different. So I think they can recognize, let's say, faster what is important and what should be done. On the Bornholm and Samsø, they managed to turn their heating to renewable heating, to install many of wind turbines onshore, offshore, and without any significant problem of local population that they will say, okay, this will turn off the tourists, or they are too close to the islands, etc. On Orkney, they also have a quite large amount of renewables in the grid, and now they are trying to set up the smart grids, because the lots of this potential is wasted, as it should be curtailed to maintain the systems. But in Mediterranean, we also have some candidates that are close to this prize. However, let's see, maybe in new winners there will be some Mediterranean islands. I hope they will announce soon who won this prize. But we have in Croatian Greek islands, we have some of these new technologies that we are applied, or for example, the pump hydro combined with desalination which can be a good solution, or PV with batteries or hybrid systems like on Tilos Island. In Croatia, we have island of Krk, which is quite the level with the vision. So they have a good vision to become a carbon neutral island. They start to build facilities, and let's say they have good results in waste management, water management. Also, they implemented several smaller renewable projects, but there are no bigger projects and a significant amount of renewables currently in the grid of the island that are being produced on the island. So this is something that that should be changed. They also are good in electric vehicles, like they are good in electric ships. On island of Mljet, we have 3 electric ships going and bringing tourists from in a national park of Mljet to some smaller islands. So we have candidates, but we need to work more systematically and help them to reach this, let's say, maximum of renewable energy penetration and to enhance this system. So in Croatia, we also put this smart island and sustainable island in our law. So in the law of Croatian islands, there is a certain article that is saying how a smart island should be, let's say, defined, and that government and law will support the projects for the smart island. We also have a lot of local sustainable energy action and climate plans, which are bringing the vision and projects that should be implemented in islands. However, as I said, this is maybe slower in Mediterranean than in northern islands, so we should to speed up the process. And if we talk about this sustainability and solutions for islands, they are not quite new. But if we look just in Croatia, you will see that 30 years ago, Professor Barber from Split University also had this idea how to convert and transform the islands in self-sustainable islands with hydrogen. So let's say 30 years ago it was a vision, but it still is not a reality in our islands. But let's say we try to work on many issues, and now with this smart approach, with integration, with ICT technology and digitalization, let's hope we will manage to go to the future and really implement this vision. So here we have many things that we need to look at. So the key areas for the development of smart and sustainable islands in Mediterranean, we divide it in just 8 topics and areas which should be followed. And here I will not go through each of them, but you can see what you should work on and what should be implemented in this island. So maybe this first slide is for technology and technological issue, but what is also more important is to take care about the governments, ICT, economy, and education. So by enhancing the ICT and use ICT, I think we can also help governance to make sustainable long-term planning, to allow a multi-stakeholder collaboration, so many people can be owners, and by also these things like also this platform for blue energy or other platforms which are allowing us to have aggregation and joining the smaller projects in the bigger one. Finally, education is also important and can be enhanced on islands. So this is something that should be now exploited, because we saw that in this virtual world and by use of many technologies that are developed now in this pandemic. We can even make islands, places where you can come to work and study, etc., and live. And on the other side, you can be connected to many more things in the world. So I will just go fast through some of current projects and results. So we try to optimize these smart islands with many methods, tools, etc. So currently we also work on automatization of the Renew Island methodology and optimization through some 40 indicators. So just to provide more scenarios, more let's say visions, but at the end the local people, local government, and stakeholders should decide which approach they want. So this is just something that will support them. And here we can see, how some technology can make difference in a certain setup, etc. So it's not something that is not done before, but let's say that we will try to see it more precisely or more automatized. Then what is important to take in the risk assessment into account for every scenario, and we can see that this is important for currently when we are also coming to development of sustainable energy and climate action plans, and to evaluate the risk of global warming and how to adopt. Similar to that, we try to measure many risks connected to electricity, energy sector, development, financing, etc. This is something that should be taken into account. As we can see that some tools bring you the optimized scenarios and solutions, but then we don't see so many changes on the ground, and as some of the risks like regulatory or financing is not taken quite well into account, etc. So this is something that is calculated. Then we are now looking more detailed in demand response, which is should provide also benefits to islands, and how to integrate more of renewables. But here we also can see that even if you have this optimized system, the regulatory framework and lots of setups like smart meters, etc., it's not fully ready at some places, so this should be further enhanced. There are also some new tools used for the planning and of the electrical grids of whole energy systems and storages, which are now being developed and analyzed. So we try to go more deeply to the special planning to get more detailed results, and in time resolution that is better suited for integration of renewables. So we can see how modeling is impacting the share and capacities of different renewables. And finally, we have also some projects that are enhancing implementations of all these things. So here we are currently working on a project in Sulaya, which is project for maximizing the innovative energy approaches on the islands, where we have 3 lighthouse islands: Unie, Bornholm, and Madeira, and follower islands. And on Unie as a island, and in the whole project we also are building some kind of reference islands, and according some indicators we want to reach to become sustainable, and also developing tools that should help local stakeholders, governments, planners, etc., to implement their solutions. In Uni Island, we are currently building a 1 megawatt photovoltaic power plant with a battery system that should show how we can together jointly run this system. And then we will connect this to desalination plant, which also has renewables, and try to manage together the water and energy system, as water energy nexus is quite important together with the food, etc. So finally, Internet of Things and 5G is coming, so there is a platform that we want to develop together with company Ericsson Nikola Tesla, which is working on these smart island issues. So we want to see how the island is behaving and to get, let's say, the best from these solutions. So finally, if we want to build all these solutions, turn our visions, our models and results, our scenarios into reality, we need a lot of young people there. So I'm also here presenting just shortly Project Genesis, which try to put young people from islands that are not in education, training, or they're not involved in work. So to switch, to try to help and build some of these solutions. My colleague Nikola is in Split, so he can tell you more about this project and maybe show what are the benefits. But let's try to make young people stay on island or come to island and try to work on these very interesting projects to build a more sustainable future. This is, instead of conclusion, I just want to thank you for attention and hope we will have a good discussion after the presentations. Thank you.
Thank you, Professor Kracic, for your interesting presentation. We will move on with our presentations. So now I invite Mr. Matteo Macanti and Mrs. Morena Bruno from the University of Siena to start with their presentation on blue energy technologies and how do they work. Both of the colleagues from the University of Siena are part of the just a moment, the ecodynamic group at the University of Siena, sorry, I had to read it, and they are working on the energy life cycle assessment and greenhouse inventory within the ecodynamic group there. So, colleagues, the floor is yours.
Thank you so much.
Okay. Can you see our screen?
Yes, everything.
Okay, perfect. Good morning to everyone. So the University of Siena developed the Blue Energy Catalog in order to describe and have an overview about a set of solutions for blue energy technologies with the highest technology readiness level. And for this reason, we classified them into three main groups. Onshore devices able to exploit wave energy, but also salinity gradient and thermal gradient. Nearshore device, such as wave energy converter or a system able to exploit marine biomass, and offshore system like wave energy converters, floating wind turbines, but also device able to exploit marine currents. Data refers to existing installation as pilot project, but also operating system. And when out of the region, we scale down data about physical requirements, technical value, and energy production in order to better fit the Mediterranean area. For the onshore environment, the first example is Oceanic water column system, characterized by concrete chambers in most of the case. In this system, incoming waves let seawater level move up and down in order to create an airflow that can move and drive some turbines in order to generate energy. These chambers can be embedded into new piers or existing one, and some interesting examples are the Rewek 3 system in Civitavecchia, in Italy, and the Motrico plant in Spain that we will see further. Here we reported some information about technical requirements, the dimension for, in this case, a 100-meter pier, and information about electricity production with some details for the rated power, the installed capacity, and the range of households that could be supported in terms of energy demand. What about the Motrico plant? It is characterized by 16 turbines for an overall installed capacity of around 300 kilowatt, able to produce more than 200 megawatt hour per year. After that, we analyzed the oscillating floater system. In this case, floating bodies are able to generate energy through the motion of incoming waves using hydraulic pistons. Also, this technology could be embedded in existing piers or new one. An interesting plant is in Gibraltar. Here, the information for technical requirements and energy production. What about the EcoWave Power? This system is testing in Gibraltar, is characterized by 8 floaters for an installed capacity of 100 kilowatt, and this plant is connected to the national electric grid by 2016. For the nearshore environment, we focused our attention on seabed-based buoy. In this case, the vertical motion of ocean waves is converted into linear or rotational motion, basically through a power takeoff system. These buoys could be installed in order to create clusters of bodies, and one example is in Sweden, especially the site of Sotenäs. Here, the same information as we saw previously about physical requirements and energy production per device. The plant in Sotenäs is characterized by around more than 30 buoys for an installed capacity of 1 megawatt, and the energy production could be around 3 gigawatt hour per year. What about the onshore environment? For the wave energy converters, we analyzed the oscillating buoy system. This floating body is connected to a piston or a cylinder mechanism in order to produce energy through a magnetic system. Also, in this case, the buoys could be installed in order to create clusters, and some tested sites are, for example, in Italy, but also in Portugal. Here, the information about physical requirements, the sites, and energy production. What about ISWEC? This device has been tested in Pantelleria, in the Sicily Channel. This buoy is characterized by 100 kilowatt of installed capacity, and the energy production could be around 200 megawatt hour per year. This device will be tested also in the Adriatic Sea in front of the coast of Ravenna. What about the marine currents? We analyzed the underwater helix system. This submerged body, bottom fixed, is characterized by a set of turbines or helixes, and the electrical generators are installed behind each rotor. Here, the information about technical requirements and energy per device. And one example, it will be tested in the Strait of Messina, is the GEM system, characterized by 2 turbines and installed capacity of 100 kilowatt. The energy production could be around 300 megawatt hour per year, but in a specific condition of tidal current. And now I leave the floor to my colleague Matteo Maccanti in order to focus our attention on wind energy.
Thank you, Morena. So the last technology evaluated for the offshore environment are wind turbines, because the exploitation of offshore wind is one of the most promising solutions to get away from fossil fuels in the next future. Now, a new frontier in this sector is represented by the offshore floating wind turbines. And this type of turbine are fixed to the seabed only thanks to mooring and anchoring system. And this allows to the exploitation of seawater with higher bathymetry until 500 meters, where usually there are also higher wind speeds. The advancement in literature and research in this sector is higher respect the other blue energy technologies. To date, the most common commercial turbines have an installed capacity between 3 and 6 megawatt, but turbines with higher installed power are currently in testing phase, even up to 10 megawatt. A single turbine, like the one we studied in our work, can generate up to 20-25 gigawatt hour per year, supporting the energy demands of more than 7,000 households. In this lab, in particular, we focused our work on two different types of floating offshore wind turbines, as I said, a spar buoy and a rough buoy device. And because the floating wind turbines are the most promising solution for the next future, in particular for the Med area, because of its high bathymetry. To date, two concepts are demonstrated in full scale. There are high wind and wind float. The high wind is a spar buoy turbine, and as you can see on the left, this technology was installed in Scotland in 2011 for the creation of a wind farm with an installed capacity of 30 megawatt, able to meet the energy needs of more than 30,000 households. As regards the rough buoy device, a 2 megawatt full-scale turbine with the wind float concept was installed in Abusadora in Portugal, producing more than 3 gigawatt hour per year. Here you can see a panoramic view of the high wind floating wind farm in Scotland. And here I show you the wind float Atlantic plant, which is the world's first wind float farm that became fully operational off Portugal in July 2020. But as today, a new frontier in blue energy is the development of integrated devices that allow the combination of different technologies for the exploitation of several marine renewable energies in a single system. The first example of a hybrid blue energy platform could be this one that integrates three different blue energy technologies. As you can see, this floating structure is covered by PV panels. It's possible in this case to install around 70 PV panels per square module with an installed capacity of 30 kilowatt. A platform like this can also host different buoys setups for the exploitation of wave energy, but also several mini wind turbines. And in this case, this platform is it can be also equipped with several storage modules. Here you can see some possible visual solutions performed by the company that carry out this device to image how these modular platforms could integrate with natural and with man-made environment in next future. Some companies are also studying other solutions. In this case, a floating wind turbine like the wind float, which I showed previously, is equipped with an electrolyzer unit for hydrogen production, starting from seawater and from the excess energy produced by the wind turbine. And in a platform like this, it could be also possible to install, for example, PV panels to increase energy production. Another example could be this one, where a floating platform hosts 4 floating wind turbines and also a set of buoys for the exploitation of wave energy. And here another project where a wind turbine with tripod foundation is equipped with fish cages. These cages are moored to the tripod foundation in order to allow fish farming. So this type of hybrid plant are at an early stage at the moment, but many possible advantages are already evident. For example, it's possible to increase the energy production rate of a specific area, but also reduce the non-production hours that can characterize some blue energy technologies. It's possible to ensure the energy independence of these platforms, but also produce and provide sustainable electrical energy for other marine activities such as fishing, aquaculture, water desalination, but also oil and gas industries, transport, etc. Could be useful a system like this to share infrastructure and equipment between different devices, but also attenuate the platform movement and so improve the stability of this platform. And this technology could also reduce some costs, for example, costs for infrastructure, for mooring and anchoring system, for transmission, for connection, etc. And another idea could be to convert existing platform on end of life, for example, platform for gas and oil extraction. So thank you so much for your attention, and let's make a blue deal.
Thank you for your presentation, both to Matteo and to Morena. We now move on to our next presenter. In my opinion, this is a very interesting presentation that will be shown by our colleague from USpace, Federica Di Pietrantonio. I apologize if I did not pronounce it correctly.
It was perfect. Thank you.
On the energy planning, environmental assessment throughout the years, and also working on different EU-funded projects and managing them. Federica,
hello.
You're next.
Thank you, Roye. Thank you for your presentation. I'll now try to share the screen. I hope it works as it did before. I think it works. Just a minute. Okay. Can you? Oh, why doesn't?
Can you put it in full screen?
Yes, I'm trying. Actually, oh, okay.
It started now, so yeah, it works.
Okay, perfect. So, hello everybody. This is, as Roy anticipated, I'm Federica Di Pietrantonio, work for USpace Spain as a consultant. USpace is a partner in the Blue Deal project, and our work focuses mainly on the energy potential analysis regarding specifically blue energy installations. Let's start from the beginning. What is our project, as it was also anticipated before? It builds on the results of the MED Maestrale project that already produced WebGIS for the visualization of the blue energy potential in the Mediterranean. Our objective in this project, in Blue Deal, is to improve and further detail the WebGIS produced by Maestrale. Another assumption was to take into account the blue energy, the Blue Deal catalog that was presented by our colleagues from University of Siena, and to take into account the minimum technical requirements for each type of blue energy technology. The final goal of our analysis was to identify that those areas that are potentially fit for the installation of marine renewable energy technologies. At the same time, we wanted to minimize the disturbance of environmentally sensitive areas and ecosystems, the interference with other maritime activities such as navigation and fishing, and the visual impact of the technologies.
what was the process that we went through? First of all, as I mentioned before, we worked on based on the GIS from Maestrale. We constructed a GIS project collecting a set of open access data related to basically to the environmental conditions that are relevant to the blue energy deployment, for example, bathymetry, wave height, wind speed, etc. We collected the boundaries of environmentally sensitive areas, and also the paths of navigation of ships movement and other relevant infrastructure that could be useful for our work. The second step, of course, was to identify, as I said before, what are the areas, both marine and also along the coast, that have the minimum environmental conditions that are required for each type of blue energy technology to operate, basically, to function. From these areas, we excluded those that we found unsuitable for the installation. For example, the areas that are especially sensitive from the environmental point of view, areas that interfere with navigation. And so we set some parameters for these exclusions and identified and sized some buffer zones around these areas of exclusion. In the end, we identified both the eligible and pilot areas. That is basically, the eligible areas are those that are fit for installation because have the minimum requirements. The pilot areas are those where these characteristics are better in a way, and so the energy potential is higher. I would like to underline that this analysis, due to the scope of the project, on the duration, and also on the data available, is, of course, preliminary analysis. So all the things, all the maps that you will see further on in my presentation are only representing the potential areas that can be exploited for these installations, but they are not in any way they are still not fully realistic, because more detailed analysis would be necessary to really think about installing something there, and also additional data would be required. This is a very short overview of the data sources that we used. It's also only basically European level and European scale, also open databases. This is the geographical framework. As you already know, our target area was the split Dalmatia County. We considered basically the marine areas that are included in the internal waters and territorial waters. We didn't consider for this analysis international waters. For wind farms specifically, we considered only areas that were more than 10 kilometers from the coastline. We started, as I said, from the Blue Deal catalog. For the split Dalmatia County, we considered 10 types of blue energy technologies, and of course, the minimum environmental requirements for their operation. Let's start with onshore devices, onshore converters. As Morena told you before, we're talking about basically wave energy and salinity gradient. For wave energy, we have three types: oscillating water columns, overtopping breakwaters, and oscillating floaters. And for the salinity gradient power, we considered the reverse electrodialysis technology. What I will show you now is the process that we followed for the analysis. So you will see a series of maps where I will underline what was done in each step. Let's start, for example, with oscillating water columns. We started by identifying in the map the areas with suitable bathymetry, so between 15 and 3 meters under the water, of course, and the areas having a wave height higher than half a meter. We intersected these areas, and the red parts that you see in the map are the result of this intersection. The second step was the identification of the boundaries of what we assumed were environmentally sensitive areas. That is to say, basically Nature 2000 areas and also Posidonia meadows that are a very important ecosystem in the Mediterranean. Around these areas, we considered a buffer zone of 500 meters, and we assumed that this area is not suitable for installation. So we excluded from the suitable areas identified in step 1 the unsuitable areas, the sensitive areas identified in step 2. And this is the result. As you see, the eligible areas are light red, and in darker red, there are 2 possible pilot areas with their surface and their environmental characteristics. The same process applied to other technologies. In some cases, like for this one, the overtopping breakwater, we found out that basically, just from the beginning, we found that the technology is not applicable in the region because the maximum wave power in the area is too low and is not able to ensure the operation of the technology. So in this case, no data is available. For onshore floaters, we followed the same procedure. Now I'll start going a little bit quicker on this. The parameters that we chose, of course, vary a little according to the characteristics of the technology, but basically the process is the same. Identification of suitable areas, exclusion of environmentally sensitive areas, and identification of possible pilot areas. Here you see the 2 more promising areas for this technology. As for reverse electrodialysis, that is to say the exploitation of the saline gradient, the procedure was a little different because basically the only assumption that we had that these kind of plants can be combined with desalination plants or with river mouths where there is a natural gradient of salinity. In the region, as far as we know, there are no desalination plants that can be used for this purpose, but there are 2 freshwater courses that flow into the sea where this kind of technology can be installed. Let's go to the near shore. As you see, we will basically talk about the seabed-based buoy and algae farms. For the seabed-based buoy, here again the same process, intersection of bathymetry and wave height. union of boundaries of environmentally sensitive areas. In this case, there is an additional assumption that we made regarding the main navigation routes that in the region are really numerous, and of course they could interfere. The blue energy source, the blue energy technology in this case can interfere with navigation routes, and so we excluded them as well. So this is the result of the exclusion, and these are the possible pilot areas with their characteristics. No data for the oscillating attenuators. Also in this case, the maximum wave power detected is too low, so the technology is not applicable in the region. And instead, let's talk about the marine biomass. Here, there were the main constraint was represented by the environmentally sensitive areas, and here again from the navigation routes. So this is the exclusion, and these are two potential pilot areas for algae farm. Of course, this is, as I said before, a very preliminary analysis just to identify areas that could be suitable. But of course, the installation of this kind of plant, as the previous ones, requires always additional investigation for another kind of analysis. Let's pass to the offshore. Oscillating buoys, tidal current turbines, and offshore floating wind. Same process for the oscillating buoys. And here again, these are the possible pilot areas. No data for the tidal current turbines that are not, the region is not suitable for this kind of technology, because the maximum current speed is too low, is only 0.3 meters per second. This was actually not a surprise for us, because as you already know, the Adriatic Sea has no strong currents, and perhaps in some places, like for example in Venice, as Matteo and Morena showed before. Let's go to the offshore floating wind. That is basically what everyone is expecting. Here are the preliminary specifications we used to conduct the analysis. As I said before, we considered a distance from shore more than 10 kilometers. For the sea depth, we considered a quite big range. And but upon request of the University of Zagreb, we analyzed, we divided our results in 4 bathymetric zones, from the shallowest one to the deeper one. As you see, the results are interestingly different for these 4 zones. We also considered a buffer of 5 kilometers around navigation routes, and also a 2 kilometers buffer from nature preservation areas. This was, we started with the first zone A, with bathymetry minus 40 meters. The first step was, of course, as you know, to intersect bathymetry and wind speed characteristics. So we considered the distance from the coast between 10 kilometers and the limit of territorial waters, for a total of approximately 23 kilometers. The wind speed should be, in this case, no less than 4 meters per second. That is the minimum requirement. And here again, we consider the boundaries of Nature 2000 sites of the Posidonia Meadows, and these areas and the buffer 2 kilometers around them will be excluded, as well as navigation routes and ports and maneuvering areas of ports and the buffer of 5 kilometers around them. This is the union of the constraints, let's say, and this is the result of the exclusion. And this is a very, very small possible pilot area. You can see it in the middle. As you see, the area is really small, but this is also for the zone A, because if you go deeper, for example, in zone B, we followed, of course, the same procedure, and the pilot area possible is quite larger, as was quite expected, actually. This is for zone C, so a little bit deeper, from 60 to 80 meters below the water level. And this is for the zone D, finally. That is definitely definitely provides more interesting results to possible pilot areas with quite good wind speed, comprised between 4 and 5.4 meters per second, and the bathymetry between 80 and 140 meters. This is the summary localization of all the applicable technology that we saw so far. As you can see, the offshore floating wind, that is the last point, can be found. The highest potential for it can be found in the south and southwest of Split. Just a very short overview of what were the main criticalities that we incurred during the analysis. The more impacting one was the difficulty in finding open geographical data that could be suitable to use in a GIS. This, of course, and especially these geographical data were not open, were not freely accessible, and sometimes they were not very detailed as regards the scale also of the data. An important lack of geodata we could find on two aspects that are very important to assess the environmental impact of blue energy technologies. The Posidonia Meadows, we found some data, but were not, we had to adapt them and to make proxies. So the effective sites of these areas should be further assessed. And also the total lack of geographical data, complete and reliable, on birds migration routes that are essential for the planning of offshore wind turbines. As I said, the data available were not very detailed, had not a very sufficient scale to go into detailing for some aspects. Of course, what we used was range values that represented the minimum requirements for each type of technology. And of course, when you choose a specific device, it is important to carry out more detailed analysis as regards the production, the continuity of the production of energy, and also the environmental impacts and the impacts on on other maritime activities. This is important, and this is another point regarding the fact that what you saw so far is really a preliminary analysis. Another thing that we learned during this project and also here in Croatia is that the involvement of local stakeholders is essential, not only to build consensus or to get to inform them, but it's also essential to collect the data, because sometimes data are available from different sources and from different institutions, both local and private, for example, associations and so on. And also, of course, it is important also to select the pilot sites out of the eligible areas, because what we do is a simulation and is a hypothesis, but this must be verified against local conditions that perhaps we do not know fully. Thank you very much. I hope it was not very boring, this presentation. I will stay available for questions when it's time for questions, and these are our contacts as you space. Thank you very much for your attention.
Thank you, Federica, for your very detailed presentation. I enjoyed it and like it a lot, and hope that other listeners were also enjoying it, and I hope we will have a lot of questions later on. So be prepared. So we are moving forward to our next presenter. Our next presenter is Konstantinos Smagas from the Geoimaging engineering company from Nicosia, Cyprus, and he will say something about the visualization of feasible blue energy technologies in Croatia, specifically for the zones that now Federica presented. So, Konstantinos, please start.
Thank you, over here. Yeah, after the flagship presentation of Federica, I will try to present you some elements of how those technologies are visualized into space. I will allow me to share my screen now. Just let me know if it works. Okay, so my name is Konstantinos Smagas. I work for Geoimaging as a company in Cyprus, and the context of this presentation, we will be dealing with an element of participation, citizen participation or stakeholder participation that is quite high on the agenda lately, and this is the visual impact of those technologies, because it's really important to know if something is feasible and where to install it, but it's also very important to collect, as Federica said previously, all the data available and necessary to make these technologies feasible, but also to see how they look into the environment, and of course to inform the participants. So I will be speaking later on for what is the objectives of having visualization exercises within the Blue Deal Lab planning process, and whether that is important or not, the methodologies and the tools that we have been using in order to come up with something that makes sense. And then we are presenting you the 3D models of the blue energy technologies. And the main course of the presentation is the visualization of the feasible blue energy technologies in Croatia, which is exactly based on what Federica presented you earlier. And then a small feedback session will follow on Slido. So, what is our approach? Our approach for the participation of the plan in the planning process, we use a simulated visual environment to visualize characteristics of selected blue energy technologies and their interaction with the landscape. And why do we do that? We do that because we want to increase the level of information on the blue energy technologies, so people have something more, something that they can navigate around, so they can view the technologies on their own. We want to increase the engagement and the feeling of ownership to the stakeholders. So we are trying to create 3D models in order for the people to better understand how the technologies work and how they function and they interact with the environment. And of course, we want to kick off a debate, which is a very, very important element of any transparent and inclusive planning process. We know that people have concerns, and we should definitely be there to consider those concerns. It's a critical element. If we want technology to be adopted, then we should empower people to climb up the ladder of participation and get into models where the citizen and the stakeholders feel that they are in control of the process. It's a very important element for the sustainability of the technologies themselves. Another very important aspect of what we are about to present here is the fact that we are introducing elements of visual impact assessment, which is somehow a part of the environmental impact assessment, and it's a systematic method. It's a systemic approach on how to figure out the interaction of those technologies with the environment and what is the people's perception of how those technologies look like. Are there limitations when we are visualizing blue energy planning? Yes, there are a lot of limitations. First of all, design. The design, we are lacking a lot of information about the technology since they are under development, and some are protected by patenting. It's a huge challenge to obtain the raw data to conduct photorealistic environment. For example, it was impossible for us to go on site and take pictures of the surrounding area. The delivery, it's really difficult there are software limitations and widely accepted technology and methodologies. And of course, it's the element of subjectivity. You know that engineers tend to get fascinated with the tools they use, and they create worlds and environments that maybe are not corresponding to the real world. For example, when we were studying working on those visualizations, this is definitely not how the sea bottom looks like, and definitely this nice tropical island cannot be found in the Mediterranean. And of course, when it comes to the evaluations, there's a huge limitation there, because the visual impact is largely assessed by a qualitative judgment. What might look nice to some people might not look nice to other people, and of course it's a very relative. So in order to proceed with the visualizations, we created 3D models first. So we took a lot of help from the catalog and all the information that is available out there. And we used different techniques to design the models. And we will be liaising with our friends in Indaco to share some models as well. So we have created 10 models so far. And we take those models and then we try to put them into the terrain. This is a more complicated exercise, because those are the areas, for example, that Federica presented us before, and those are the areas that we are conducting a visual impact analysis. We're using the viewpoint perspective. So we pick up selected areas in the map and try to imitate how the technologies might look like in the horizon. We have been using the Unity game engine, so everything has a great deal of animation and an element of gamification, but this allowed us to use virtual real worlds in order to create the perception of distance when it comes to the human eye, and of course use data and different layers of terrain and elevation. So in terms of data, it's quite a detailed analysis. If you could see here on the methodologies, in the grid, the wind turbines have been placed roughly to 900 meters from each other into distances that are completely eligible for the areas. So trying to imitate, of course, with all the being aware of all the limitations, we try to imitate the real environment. And going back to the technologies, feel free to visit our exposition of the blue energy technologies. I will be now to. This is the element of the Blue Deal Med website with the technologies. And for example, if you would like to see how onshore wave energy oscillating water column works, we have created models of it. You can navigate with that, and you can investigate different environments and different technical descriptions here. And of course, you can go to other technologies. This applies, and all the technical description is here. This is part of the process to enable the users to get familiar with the process. Getting back to my presentation now. So and away from the we took the 3D models, and then we focused on the area that Federica mentioned before, trying to replicate the park that has been eligible. The University of Zagreb will speak later on about the overall productivity. We're going to be presenting you two wind farms. One that is the smaller one that is west of Korčula Island, with 34 spar buoys, a second wind farm with 265 spar buoys wind turbines. And we also selected two other technologies, the oscillating floaters and the seabed buoys. Not for those technologies, not a full analysis has been conducted, obviously, but we thought would be very educational and quite nice to play around with them, since they can be installed much closer to the shore. Of course, their potential is much lower. However, when the conditions are allowing that, they could be widely used. So, okay. I'm going to be presenting this to you via a film in order to save time. So, I don't know, Jorge, can you see the video here? Yes. Okay.
Sorry for not being here.
Not a problem.
Some technical issues.
Yes.
We can. I can. If you can start the video.
Yes. Can you see it?
Yes. Now it's. But
great. So first, this is the first potential area. As you see here, we have been using the Unity environment. This is the park with the 34 turbines. It's 15.2 kilometers for Korčula Island. We had an eye to create a nice animation and gamification environment, because this tool is primarily to be used for educational purposes as well. So this is the first viewpoint. It's 60.2 kilometers. The camera elevation is 500 meters, so it's It's above the ground. You can see a bit of something moving in the horizon. So when you use the binocular effect, it's definitely there. This is the third point view. So definitely you can see something in the horizon. It's not very visible, but it is still there. This is the second park. There's a much bigger one here. It's 265 turbines. This is the biggest one that the area can sustain. This is the view from the sea. We have a mock-up with our fishing boat. The first viewpoint, 15 kilometers from the shore, northeast. You can see that the park is occupying a great deal of the horizon. The second viewpoint, southwest from the park. And yeah, this is the viewpoint. Of course, this is a really quick video. You can visit everything on the tool. This is the oscillating floaters. That's much closer to the shore. It's surprisingly how close can it be. It's even people who can swim well, they can reach it. This is an indicative technology, just to have an idea. It's 1.9 kilometers from an elevation of 29 meters. This is how they look like. And something closer to Split that is eligible. It's from a nearby suburb area. If I can see correctly, this is how they work on the bottom, from the 48 meters elevation. That has been a quite quick presentation and maybe not too detailed. However, if you would like to have a look and go through the tool again, you can visit the tool. It's here on the Blue Deal Med platform. It's also available through the link, and you can navigate in a nice way around, and you can change the technologies. We have a drone and a boat perspective as well. Closing now, moving to the presentation, I would like to run a small exercise with you. This is the feedback session. Please feel free to scan the QR code. We would really like to know what you think about blue energy technology use and their visual impact into the areas. Scan the QR code or click on the link at the Q&A session. I will be directed now to the...
Just please wait a moment with the scanning of the code. So if you return it, give a moment or two.
There's also a link in the Q&A section of the on the Blue Deal Med platform. On your right side, there is a Q&A. You can click the link, and this should work.
Okay, you can continue. Thank you.
Okay, thank you over here. So.
Konstantinos,
yes.
It says that voting is closed.
Yes, it's closed because I'm starting right now.
Okay.
So, what do you think? How concerned would you be regarding the visual impact of blue energy technologies? What do you think? Is it something that it's affecting people's opinion? Okay, votes are coming in. 13 people voted so far. People are definitely seem to be concerned, moderately concerned. Come on, tell us what you think. It's completely anonymous. Okay, great. So from 16 votes from the audience now, yeah, people are concerned or moderately concerned. So this is something for us to definitely consider when we are planning for blue energies in certain areas. This is something that we are well aware of. We came across these issues in previous Blue Deal labs. I will move on to the second question. How important do you think is the visual dimension? For example, the use of 3D models as a tool to inform participants during a blue energy planning process? Of course, in our case, it was really difficult for us to construct a photorealistic environment, since COVID did not allow us to be in Croatia and take photos from the horizon, photos from the environment. We had to use virtual data. So people think that's very important. That's good for us to know. Of course, we definitely have to improve the methodology, but since visual impact assessment is part of the environmental assessment studies, I think it's going to be used more and more in the future. Great, thank you guys for voting. Now moving on to the next one. This is a free text. Question. What do you think is the biggest challenge when it comes to blue energy planning in your area? Go on, text whatever you think it's important. It will be presented here on the screen. I know in previous labs we have public acceptance. Yes, social acceptance. This is important. This is definitely a message, a key message for us to take home. Arvoy, I'm sorry, I'm taking a bit of your time here, but I thought it would be
no problem, because this is very important, and
yes.
I share the opinion with the public acceptance. This is very important, and I can see that they are highlighting the importance of this issue, and that's why we are doing this lab, to share the knowledge and disseminate the knowledge with the general public.
Absolutely, I agree with you, and we should view our role like that, I think, and especially with when it comes to communicating scientific data. Lack of data, lack of methodologies, bureaucracy, cost, of course, the policymakers' ignorance. I just hope those people on board today are not offended. But information must be on the table. Tourism, intersection with tourism. I think we will let it there. It's going to go on and on. However, let's keep it here. This will be part of the results of the lab. Of course, the environmental impact and public acceptance is definitely seems to be prevailing here. Thank you, Jorge, for allowing us to make this presentation, and I give the floor back to you. Bye-bye.
Thank you, Kostinos, for your nice presentation and the visualization of the possible locations in the split Dalmatia County. As we saw from the slide of results, this is one of the key issues with the novel technologies, the public acceptance, and how to disseminate the knowledge, the scientific knowledge about the blue energy technology with the general public. Now we continue with our agenda. We are going to our next presenter, Mr. Hrvoje Stancin from the University of Zagreb, and he will tell us more on the introducing of the blue energy potential into the Croatian energy system. So to see on the now previously shown possible locations from U-Space, what is the potential energy production from those sites. So, Mr. Stancin, the floor is yours. Okay.
So hello to everyone on site and online. I will present the results regarding the blue energy potential assessment for the case of Croatian energy systems. So to start, first of all, the input data was built for 2018, which was the year that we have the most data for. As Federica already pointed out, we have problems with data acquisition for the Croatian cases. So in this case, we also had to use various documents to provide, or at least try to provide as much as comprehensive as it can be. So we used the annual energy report for Croatia from 2018 provided by Ministry of Energy and Environment, then from the Croatian Energy Regulatory Agency. And for building up the future scenarios, we've used the guidelines for energy transition for Republic of Croatia until 2030 with a view to 2050, even though we considered only 2030 in this presentation, while for 2050 there is more work required. And for the missing data, we used the data that were provided and built up in the ResFlex project, which was carried out by our research group. Okay. Okay, thank you. So the input values are all in terawatt hours per year. The most important one is, of course, the electric demand, which is 19 terawatt hours, of which heating and cooling takes 2.2 terawatt hour per year. It's important to subtract these two values because they are showing great seasonality, and then they might influence the system stability. Besides, the individual heating system demand is terawatt hour per year. This is for households and individual boilers. While in Croatia, we also had quite high share of district heating systems, which is not presented here in these results. I will explain why a little bit later. And here I put the data for industry and transport because these values are not that important when it comes to introducing the blue energy into Croatian energy systems, but are important to build up and validate the reference scenario. Okay. So energy supply system in Croatia and model validation. As you can see, the Croatia already has quite sustainable electricity production system because the major contributor is our hydropower plants, both dammed and runoff river, and they account for more than almost half of the not almost half, but quite high percentage of the total electric demand for Croatia. Here I just put the values for the referent case, which are the values obtained from EIA, Eurostat, or other documents that they provide this data regarding the production, actual production. And in the third column are the results from the energy plan, just to show that results from energy plan and from the data that we have are greatly correlating, and the difference is 5 to 10% depend on the energy source. And of course, it is important to say that Croatia has really good interconnection lines with bordering countries with total capacity of 4,000 megawatt. Which allows greater penetration of renewable energy sources, and also at the moment Croatia has quite high import, 8.7 terawatt hours. That should be not gigawatt hours, and fixed export is 3.16 terawatt hours per year. And in general, this difference between import and export is 5 terawatt hours on annual basis. Of course, here you can see the great capacity of thermal power plants which are using natural gas. Actually, these are not thermal power plants solely for electricity production, but they are combined heated power systems. Onshore wind is fairly presented, even though it could be better, while the PV is poorly presented. So renewable scenarios for 2018, we built a scenario taking into account the reference case for 2018 and introducing the offshore wind. While for 2013, we consider the energy transition scenarios with energy efficiency and stronger penetration of other renewable sources. And of course, again, once again, offshore wind. Here on the third bullet, you can see that energy transition implies electrification of individual heating, especially for households. greater penetration of electric vehicles, phasing out coal thermal power plant, and reducing the usage of other thermal power plants if there is a better way to produce electricity from renewable sources. And of course, reducing the usage of fossil fuels for households heating and cooking, even though this might be a little bit challenging for some areas. So the next one, please. Here, this is a picture that already Federica showed. I just put it here on the left side, the preliminary assessment that we carried out for the whole case of the Croatia. And also from the Croatian Hydrocarbon Agency yesterday, they showed that there is a great potential on the northern part of the Adriatic Sea. And this is even better because the bathymetry is over there greatly better, and the sea is shallower. So this is quite okay. But for case of the Split Dalmatian County, these are the locations that were selected here around the island of Vis. And I'm not sure if you can see clearly, but for the north area, the north area has 800 square kilometers, and the south one has 263. The bathymetry over there is between 80 and 140 meters. So offshore wind farm, we consider the nominal capacity of one turbine that has 6 megawatts, and we took the 3 square kilometer as a zone for each turbine that it can be installed. This could be maybe a little bit less, but we took this as a safety factor. So on the north area that was shown on previous picture, you can see that we can install 265 wind turbines, which would be slightly below 160 megawatt of installed capacity, while for the south area, this is a 34 turbines with slightly above 200 megawatt of installed capacity. So when we have this number and when we have distribution curve for wind speed, which was provided by our partners from CRES, we performed the analysis in energy plan, and the results were that estimated electricity production on the north side could be 3.85 terawatt hours on annual basis, while for the south side this would be slightly above half terawatt hours per year. And average load factor is 28%, which is slightly better than for the onshore case. This is the annual electric demand for Croatia. Here you can just see that demand is more or less constant during the year, with slight peaks during the winter months. And during the summer months, this is due to the electric heating and cooling, which I already emphasized before. But even though this is not that much difference, so the electric demand is more or less constant throughout the year. Here, this is the annual offshore wind production for both considered sites. Here you can see that where the curve is cut off for example, here for the north side at 1,600 megawatt hours. That means that the wind turbines are working in their full capacity. The same is for the south side, where the curves are cut off at 200 megawatt hours. I'm not sure, probably you cannot see that clearly, but in general, the load factor is throughout the year, especially during the winter months, quite good, while during the summer months, not that good, but also the production is not negligible, and it's quite significant, especially since we analyze the maximum possible capacities for both sides. Here is just the distribution curve for wave energy potential. As already Kostas pointed out, we didn't carry out the energy analysis regarding the wave energy, because the potential is there is no actual potential, because here from the distribution curve you can see that these peaks that we have Actually, I'm not sure if this is actual potential at these moments, or this is some not error but some disturbance in measurement data that were taken. But in general, not to go into too deep, the wave energy potential for case of Adriatic Sea is really, really low, and this is a consequence as the Mediterranean as whole group is already closed, while Adriatic Sea is then also even more closed. So the wave energy potential is really, really low. Here you can see the monthly production from offshore wind farms. As I already said, the greatest potential is during the winter months, while the lowest potential is during the summer months. Distribution curve for both considered sites are quite similar, not the same, but quite similar. And therefore, the trend for the monthly production will be more or less similar for both sides, even though on south side is greatly lower available area for the deployment of offshore wind turbines. But combined north and south side with full potential used, it could provide 4.3 terawatt hours of renewable electricity on annual basis, which would make it the second most important renewable energy source behind the hydropower plants. And therefore, we can say that, and take into account that this is only for Split Dalmatian County area, not for the area of whole Croatia. So this means that offshore wind potential is really could provide a good picture for the electricity production in Croatia, and it could make great impact on the whole. Here is also just to show it, more or less what I already explained now. On the first column, you can see the electric demand throughout the months and throughout the 1 year period. And then you can see the production from variable renewable energy sources, wind, PV, and wind offshore. As you can see, share of variable renewable energy sources in total electricity production and consumption could be up to 43% during the March. Which is a great result. And if you add here the hydropower plants, actually Croatia could have, during the March at least, could provide 100% of clean electricity to its distribution system. The situation is a little bit reversed for summer months, and especially in July when the offshore wind potential is the lowest. And the share of variable renewable energy sources in that case would be 70%. Here is now, you can see the share of production by these renewable energy sources that were considered. In 2018, as it was already said, hydropower plants are the dominant source. Wind is fairly used, but it could be greatly better. PV is really poorly used, and on this it should be done greatly more. But when it comes to the blue deal scenario for 2018, this is the middle part, you can see that offshore wind can greatly increase the renewable share in total production. And if you go to 2013, when some energy efficiency measures are taken, and where additional capacities for PV and wind onshore are added, the electricity production from Croatia could completely satisfy its own needs. Since you can see here, I forgot to put on the axis title, but this epsilon axis is terawatt hours per year, and you can see if the electric demand was 19 terawatt hour per year in 2018, for 2030 it is expected to be a little bit decreased. And you can see here that in this case Croatia would completely satisfy their own electricity demand from their own sources, and even more from the renewable energy sources. And here, just to support some of the, and also to show the bigger picture for electricity sector, for energy sector, you can see that introduction of renewable energy sources, or at least offshore wind, would not have that much great impact on fuel consumption as a whole, since the fossil fuel consumption is greatly present in transport and industry sector. which requires more careful and complicated planning to reduce the need. But for example, the introduction of offshore wind could completely reduce the usage of coal and could greatly help in phasing out the thermal power plant in Plomin. While in case of the oil, for example, this is more dependent on the transport sector. In case of the natural gas, since it's expected that natural gas will be used as a transition fuel, especially for industry, this consumption will increase. And in general, this is the thing why I said that to observe the system as a whole, it requires more and more work. But offshore wind can at least help us immediately in phasing out the coal thermal power plant in Plomin, which would also be the great result, since this is possible to do tomorrow. And also you can see that the energy sector is in general not the major concern, but the transport and the industry are, since they are highly dependent on fossil fuels. And here you can see the biomass. The biomass is a dominant renewable energy sources in households for case of the Croatia, and demand and consumption of biomass will at least more or less be at this level for some time now, because it's the cheapest source for majority of the population, and for this reason demand for biomass will be at this level more or less. And now just to see the sectoral fuel consumption, I won't spend much time here, but it's necessary to emphasize that energy sector will undergo the change of paradigm, how it's working now. It will be more focused on day-to-day trading on the bourse for electricity. And in general, it will be more focused on variable renewable energy sources, which then requires more careful grid balancing and stability to maintain. Households are expected to be the greatest contributor to the decarbonization scenarios. First of all, through energy efficiency measures, but also through efficient electrification of, for example, heating. Which again, for the case of the coastal areas, could be effectively done by introduction of seawater heat pumps, which are already used in some cases, but more or less they are used for some greater facilities or bigger facilities, while the usage in the households remain unused mostly. But the transport and industry sector once again will be the most challenging one. But since it's expected that electrification will take a great portion of this decarbonization strategy, it is absolutely necessary to start considering all offshore wind capacities that might be exploited in Croatia. And here now you can see the rest share of production. Once again, what was already said, installation of 1,000 and almost 100 megawatt of offshore wind farm can ensure 4.3 terawatt hours of clean electricity. But in general, the renewable energy share in primary energy supply won't be that much influenced by this factor. But the renewable energy share of electricity production is greatly supported if we introduce the offshore wind farms, since they have great potential. They have quite satisfactory load factor even in this moment, and they can provide more than of course with other renewable energy sources. They could account more than 90% of production and consumption of electricity in Croatia, which would be remarkable results. And now this is just the preview of economic assessment. Here you can see that investment costs for offshore wind farms are 1.8 million euros per megawatt. These are the data which are taken from the data set for energy planners, but these investment costs are going on the reduction almost on not daily basis, but because the cost reduction is quite often, and it is expected that these costs for installation would be even lower. But the problem for our case is that we have not great, but we have big depths at these sites that we've considered. So offshore floating infrastructures are absolutely necessary to install the wind farms over there. If the electricity price on the wholesale market could be 55 euros per megawatt hour, which was average price for 2090, the profitability and return of investment can be achieved after 19 years at year 20, which is quite, maybe at this first sight, it's quite a big, long period. But once again, as I said, this investment cost can go under significant reduction. And also the introduction of some feed-in tariffs could help us in achieving better revenue side and achieve better profitability in shorter period. But also in this assessment, we didn't consider the savings that could be derived from the savings in CO2 emissions. So in that case, this profitability would be achieved in a shorter period. And just to get back a little bit to the picture that I already showed, here on the right side, even though this was not the focus of this work here for the Split Dalmatian County, but here you can see that what would be the total capacity for offshore wind platforms. And here you can see from the preliminary assessment. And for example, for the D areas, you can see that our preliminary assessments show that it could be 2.1 gigawatt of capacity installed. And when Federica and the U-Space team carried out in-depth and detailed assessment, this was reduced to 1.8 gigawatt. Yeah, this shows that even though the total capacity might not be 10,000 megawatt, but it wouldn't be much lower. And once again, if you take a look at this table, you can see that for the A, B, C zones, the bathymetry is greatly better. And for example, in this northern part of the Adriatic Sea, the deployment of offshore farms could start almost immediately because we already have the technology for this. And now just to finish up with some specifics for Split Dalmatian County, since this is our pilot location. And the first idea was to carry out the energy planning activity for only Split Dalmatian County, but this doesn't make sense because the Croatia and in general the analysis of energy system on this regional level will not show us something revolutionary, because different was for the Crete case when we had the isolated system. Then it was really great to see how does offshore capacities influence this grid stability. But for our case, this is really not necessary, especially since the electric demand for Split Dalmatia County is 1.6 terawatt hours per year. Already today, they have installed renewable capacity of more than 1,000 megawatt, which are producing more than 3,000 gigawatt hours of clean electricity per year, which is mostly derived from hydro. But once again, just to support the thesis that why it doesn't make sense to carry out the analysis only for this regional level. One also specifics for Split Dalmatia County is that there is a huge demand in transport sector, especially navigation, and therefore they should consider also now at this moment how to maybe electrify these navigation routes, since the islands here are not that far away, and this might be done quite effectively. And yesterday somebody mentioned if the industry representatives are interested in these offshore facilities and offshore infrastructures, when since up to now they didn't see interest in something which is their main area of work, which is like navigation or shipbuilding. It's quite hard to expect that they will see interest in something like offshore wind infrastructures, but hopefully they will prove me wrong. And finally, of course, seawater heat pumps have great potential here for the decarbonization of heating and cooling sector, especially on the islands, which was not that much analyzed in this part, but this would really help for the future work. And thank you for your attention. Let's make Blue Deal.
Okay, Hrvoje, thank you for your presentation. So I would just like to say that, first of all, the units were missing on the charts and the tables, so we should have the units on each of our table to follow it more easily and to understand it more easily. The second thing that Hervé forgot to tell is that for the Adriatic Sea, the complete area that was priorly considered was for the exclusive economic zone. So this is different space that was considered for this lab. For the lab, we only considered the territorial waters and for the split Dalmatia County. So these are more detailed results and more, let's say, reliable ones. We continue with our presentations. We have to because we are a little bit late with our time schedule, so I apologize for that, but it was interesting to hear the previous presentations. Next in the line is Dr. Riccardo Polselli from Indaco 2, and he will talk about the blue energy for carbon neutrality. Riccardo, are you with us?
Yes, can you hear me?
Yes, so please start.
Okay, thank you, Roy. Thank you very much for the presentation. I have the chance with my presentation to make a sort of wrap up of what we already presented this morning. What you see in this slide in particular is the blue energy planning framework that we organized in the Blue Deal project, combining the competencies and skills from different Blue Deal partners. The process is quite clear. We start from the analysis of the marine energy potentials and the constraints in terms of regulatory restrictions or the overlaying with other marine activities and marine infrastructures. And we combine this information with the minimum requirements for the installation of each technology that you have seen in the Blue Deal catalog. The matching of this information allowed us for providing a sort of blue energy planning map and identify the most suitable sites for the installation of blue energy plants. And finally, we made some assessment from the life cycle assessment to the assessment also of the visual impact we have seen of the proposed technologies. At the end of this process, the Blue Deal project, we provide a sort of guideline of this blue energy planning process that will allow for replicability in other areas of the Mediterranean. So let's see more in detail what happened in this specific blue energy lab in this split Dalmatia County. First of all, we started for the analysis of the potentials. As said before, our main reference here is the Maestrale WebGIS platform that is an open source WebGIS, and it's quite useful to understand what are the basic requirements in the Mediterranean, or the basic potentials in the Mediterranean areas. But also in the case, in this case, we provided site-specific information concerning the potentials of offshore wind and waves in the county, provided by our partners Enea and CRES. Also, UNICE made a sort of a survey of the existing technology with the highest technology readiness level, and we provided the basic requirements for these technologies. USpace made a sort of matching of this information, considering the limitation due to protected areas, regulatory restrictions, physical restrictions like the bathymetry, for example, or the presence of infrastructures and other marine elements. And we were able to identify the most suitable sites for the installation of the technologies. And in particular, we focused on the most promising technology, that was the offshore wind floating farm. Also, you have seen a sort of analysis of the visual impact or landscape compatibility of these technologies that is quite important for the engagement of local stakeholders, including citizens, to understand the impact, the visual impact of the technology. But in particular, we should make a comparison with other infrastructures that are already existing in the Mediterranean, like oil platforms or big harbors, or even infrastructures for tourism that in many cases are ugly enough to be taken into account for a comparison anyhow. The last presentation was quite exhaustive about the potentials in terms of electricity production of the two sites that were identified for the as a location for the floating windmills. And in general, these two sites would provide 4.36 terawatt hour of electricity per year, that would cover more than 20% of the current electricity demand in Croatia. We made also an additional assessment. We considered the two basic standard technologies for floating windmills. These are not technologies provided by one specific company, but they are a standard, so a sort of benchmark for the analysis of these technologies. And we took into account the entire life cycle of each of these windmills, considering the use of energy materials, the manufacturing of all the different constructive elements, and the assembling, and finally the maintenance and end of life. And based on the life cycle assessment, we could understand what was the carbon footprint of the installation of wind farms. So combining the information of the carbon footprint and the electricity production yield, we found this final result. The final result is the carbon intensity of the electricity produced by the offshore windmills, that is from 30 to 44 grams of equivalent carbon dioxide per kilowatt hour. That is in line with any kind of renewable energy source, and is especially much less than the carbon intensity of the current electricity grid mix in Croatia. Also, I took a look at the national inventory report of Croatia, and we see that the emission of energy is the most important source of emission of greenhouse gases. It covers almost 70% of the total emission in this inventory. The total emission of the energy sector is 16,000 kilotons of equivalent carbon dioxide. And we can also compare this value with the existing capacity at the national level of absorption of carbon dioxide from the atmosphere by the local ecosystems, that is 5,000 kilotons of carbon dioxide, much less than the emission provided by the energy sector. If we focus on the electricity production, this would be half of the impact of the energy sector. The impact of the electricity production in Croatia is around 8,000 kilotons of equivalent carbon dioxide. This is due to a good share of renewables, especially hydropower plants, but there is still production from oil and gas. And also we have to consider an additional quantity of electricity that is imported from other countries. And what about this number? What does it mean, this 8,000 kilotons of equivalent carbon dioxide? We can visualize it in terms of an equivalent surface of forest land that would be needed to absorb that quantity of emission. And this forest land would be 12,000 square kilometers. What you see in this map is exactly at the same spatial scale. So that is the dimension of the forest land that would be needed to absorb the impact of the electricity production currently in Croatia. And this is the result we can achieve based on the offshore wind park that would decrease this forest land and these emissions by more than 20%. So the avoided emission due to the installation of this wind park would be 1.6 thousand kilotons of equivalent carbon dioxide. That is that surface of forest land, if you want to visualize it. So at the end of the process, we can find that we have a couple of possible perspectives. One is in the short term, the 2030 horizon. And in this case, the offshore wind can be an option to reduce the carbon footprint of the energy sector. Also, in this case, some policies concerning energy saving are very important, considering technologies, for example, in isolating buildings, but also changes in behaviors of people to improve energy saving. For example, in the case of the mobility system that is still based on fossil fuels, and there will remain an important impact due to fossil fuels. So in the long term, in the horizon 2050, we can imagine that we should plan a progressive transition to an electric society. For example, using heat pumps for heating buildings, or using electric mobility. And in this case, new renewable energy sources can be an important option. We can imagine that in 10, 15 years also, wave energy converters will achieve a good level of technology readiness level and can be an option, even if we have seen that in the Adriatic Sea this potential is not very high. We can take wave energy converters among the possible options in the long term to be implemented for improving renewable energy sources and decrease the carbon emission at national level, achieving this goal of carbon neutrality by 2050. Thank you very much for your attention.
Thank you, Riccardo, for your presentation. It was an interesting one. We will have to move on quickly to our next presenter, since we are late with the time. Now, the next presenter is Mr. Boris Ćosić, the director of the Center for Technology Transfer from Zagreb, and we now finished with the Blue Deal planning activities. We will now go to the virtual study visits, and Boris will present us the implemented blue energy technologies that were done on the Croatian coast. So, Boris, the floor is yours.
Thank you, Hrvoje. Hello to everyone, online and here. So I will, because my presentation is already finished according to schedule, I will go quickly, and you can find more information online about the topics. So I will present project Adrian, financing from the Adrian program, calling the Sea Adrian, fostering diffusion of heating and cooling technologies using the seawater pump in the Adriatic Ionian region. I will present you installation process and operation process of our two pilot plants, one in Dubrovnik and one in the city of Crikvenica. The most important thing that in the Dubrovnik pilot plant is built in the UNESCO protected building. So this is the actual very good impact of the project, showing that even in the protected building, installation of such technology is possible. So, as I said, project is funded by the European Regional Development Fund and the IPA 2 instruments. We have 6 partners from Croatia, Slovenia, and Albania and Greece. We also have at the beginning 2 partners from the Italy, but they, because of some problems, they left the project. And as I said, the main objective is to establish transnational network seawater heat pumps. So we have installed 3 heat pumps, 2 in Croatia, 1 in Greece. And we are looking for the companies interested to join and to share findings from the operation of our pilot plants. As I said, implementation of pilot plants, one of our main goals. So we have 2 in Croatia, 1 in Greece. At the beginning, situation was 1 in Italy, 1 in Croatia, 1 in Greece. But because the partner from Italy left the consortium, we had the 2 pilot plants in the Croatia. Why heat pumps? Efficiency, we can say environmental friendly. We can have, say, renewable energy source. Some advantages, we can have a lower operation cost compared to the traditional system. Some disadvantages, we can have higher implementation costs compared to the traditional technologies. What is happening now? What is the current situation? As you can see, the number of installed heat pumps is increasing. And on our last webinar, I heard that they're expecting 50 million units until 2025 or 2030. So the number is increasing, and it will be much, much higher in the next few years. So this is just to show you seawater heat pump potential, the depth in the meters. So you can see Adriatic Sea is have a large depth, so it can have it's good for the heat pumps. North part of the Adriatic Sea can have the problems, and because of that, installation in Italy, like Trieste or Venice or in Slovenia, need to have additional analysis because of impact of the water temperature during the summer period, because it's very shallow and it can have very high temperature in the summer period. And the most important thing is this: we have a very stable temperature during the year. And for example, in our pilot in Crikvenica, in February, we had the 16 degrees temperature of the water used for the heat pumps. So in our project, we wanted to install we wanted to measure our data to get comparison between the different pilot plants. So we installed the different measuring equipment in order to collect data. So I will only focus on Croatia. We have the third one is Greece. That's not part of this presentation. So as I said, Rector's Palace in Dubrovnik, UNESCO protected building. It's a low temperature heat pumps. In Crikvenica is a specialized hospital. We are heating seawater pool and hot tubes, and it's a high temperature heat pump. So Crikvenica is around 40 degrees. In Dubrovnik is around 40 degrees. In Crikvenica is around 65 to 70 degrees. Pilot plant in Dubrovnik, you can see a location where it's installed. It's installed in the basement of this building. On this location, we had the heat pump built in 80s, but they didn't. It was very bad maintenance of the pilot plants, and it created a lot of problems. And during that period, in the last 30 years, they changed heat pumps, installed heat boilers, and increasing a lot of electricity consumption and the temperature in the rooms. It was like 50 degrees in the rooms where the old heat pumps installed. So this is the old system. One interesting thing is it's a size of 600 kilowatt, and one interesting thing is installation of. They had 40 cubic meter of storage because heat pumps built in 80s, they operate in 3 tariffs. During the night they have the cheap electricity, and during the day they had cheaper electricity. So in that period they used to fill in storage with hot or cold water, depending on heating or cooling. When we started to developing our project, we found out some problems. So how to fit the heat pumps inside? We had a very narrow space or doors where we needed to pass. So, and the first design was to open the roof, but then the conservator said it's not possible. And instead of installing 3 heat pumps at the beginning, we needed to install 6 smaller units in order to pass through these doors. So installation is around 6 units, 70 kilowatt installed units in the city of Dubrovnik, and the sea intake is in the city port directly, and because of that we have higher temperatures in the summer and lower temperature in the winter. So this is the after the installation process. So pumps, electricity, storage. This is the 6 units installed, and at the moment we are using basically 2 units or 3 units depending on the demand. But we are looking to expand heat and cooled area in order to increase the capacity of installed heat pumps. So this is the just a very simple calculation of the COP. Heat consumption, electricity consumption, and how our heat pumps working. So as you can see, we are between 3 and 4. It's around 3.54 COP. It's total COP. We are calculating with total electricity consumption. You can see here delivered heat on the next graph, and consumption of electricity. At the moment, it was around 500 kilowatts hour per day consumption of our units. And on lower diagram, you can see the operation of the heat pumps. Typically, 2 heat pumps are only operating, and sometimes the third is on when it's low temperature or high temperature, depending what is needed. And you can see the different heat pumps are operating in order to have same number operating hours to have same usage of the heat pumps. So this is the first quarter of the 2021. Electricity heat delivered, as you can see, February it was very cold period, and we had a lot of heat delivered in this period. So our second heat pump is installed in thalassotherapy in the special hospital in the city of Crikvenica. We installed a high temperature heat pump, heating around between 65-70 degrees. The reason for that, because our heat pump is integrated with existing heating system. You can see here on the left side, they have 2 boilers, so 1.5 megawatt fuel oil boilers. And the problem is that during the summer, these boilers are on and used only for 100 kilowatt to heat this system. And we said, okay, we will install our heat pumps, and on that way we will try to remove boilers during the summer period, because we calculated that almost 30% cannot be correlated between heat boilers standard efficiency and consumption of fuel oil, because on boiler operating on 100 kilowatt efficiency is not like 90 and more percent, is much lower, and because of that they're using more fuel. So you can see up on right is the place, H building. Down you can see the intake of the water. It's a well, and you have 60 meters long pipes to delivering the water inside, and you have inside the pump pumping to the room. So just quick how it's looked like. I know that you cannot see all details, but basically we installed 2 big storage. We have heat pumps, and the second step in our project is to installation of the solar collectors in order to move as much as possible our heat pumps in the night mode working and during the summer, during the day to have hot water produced by solar collectors. In February, they had 60 degrees in storage by using solar collectors. So it's enough, almost enough to operate system in this period. So this is the installation of 6,000 liters of storage. So in this storage directly go hot water or cold water from the heat pump. In our case, it's operating only hot because we are heating in this winter and in the summer our pool and hot tubes. And this is after the installation. On the left side, you have storage 6,000 liters. On the right side, you have inside storage 1,500 liters. And this is in middle is the connection between big and small storage. So this is the inside. On the right picture, you have 50 kilowatt of heat exchanger, titanium heat exchanger. And this is the connection between seawater and circle between the exchanger and the heat pump. So this is how the system look like, the operation. This is very interesting. You have it's 50 degrees showing in the big storage. The reason for that was because one part of the heat pump was shut down, and we didn't notice that it's not operating correctly, but managing to operate. And what is the main finding of operation? After the installation, during the installation, we calculated how it's operating and everything, but we didn't take into account that between 7 and 9 in the morning, actually in 7:30, they are cleaning filters, and during this process, they reverse process, and they're using water from the pool, and they're taking the fresh water into the pool, and because of that, you can see they had like 200 kilowatt they need in this period. And now we are actually trying to move process of the cleaning in the evening, that the heat pump heat water during the night when the electricity is cheaper, and we have a longer period to heat our pool. As I said, our second phase is installation of vacuum solar collectors, which will help our system and increase efficiency of our overall system. So I will this was the operation of our heat pumps of our pilot project. I will just go and present very shortly about our strategy in the Sea Hadrian project. So not just installation, we also needed to summarize and create like a strategy of the Sea Hadrian project. And we built this strategy from a different type of deliverables in order to present what was achieved in these deliverables, achieved in the process of implementation of the pilot plants, and a summary of this is our common strategy. So we have the SWOT analysis in our strategy. I will not go in the details, but we try to put elements which we think that are important for the opportunity, strength, weakness, and threats for the installation of the seawater heat pumps. We also work on the S3 goals to find out and to help in the development of national legislation, regional legislation, what are the hot topics in S3 goals. We also developed the long-term goals in our strategy, policy framework, financial, technological, and social framework. We try to summarize everything as a long-term strategy goals. And at the end, we have short-term action plan, like what we think that is important to implement in next 5 years. And number one, establishment of National Heat Pump Association. We think that it's the most important. And why we are thinking for that, because in the project, during the implementation of the project, we founded Croatian Heat Pump Association. And a few weeks ago, I had a call for the establishment of Slovenian Heat Pump Association, because all of these associations are member of European Heat Pump Association, and it's much better if you have one association in your country and different companies are members. And this association is actually communicating with European Heat Pump Association, but also communicating with the national government about the problem of installing, about data and things like that. So this is what we think that is the most important in the short term and what we can achieve in this short term period. So this is all for me. Thank you very much. And for the question, please feel free to contact me. Thank you.
Thank you, Boris, for your nice presentation that included the both study visits. So I will just conclude with the virtual study visit to the Marina Castella. Their representative is not able to be with us here. They invited us just to see the location, so I took the pictures and made a presentation in their behalf, and they said that they are grateful for showing the presentation to the wider community. So I will be quick since we are a little bit late with the schedule. So this is the Marina Castella. So basically it has more than 400 berths with the electricity connection and water connection. It has 200 dry berths for ships, for ship accommodation on the land. It has also a lot of parking space, one of the bigger marinas on the Croatian coast. Their now company goal is to go to the sustainability of their business. One is with providing the electricity charging stations for their customers, for the electric vehicles. And the next steps, what they did, so what they already implemented, is for the two circles, the two buildings that have been newly built. It's the one is the upper circle is the indoor swimming pool building, where the heat pump system is installed, and the second building is the sailing club and the yacht club and the restaurant, which is also using for its thermal energy the heat pump system. So these the two major consumers of thermal energy are provided with the heat and also for the cooling purposes for the from the seawater heat pump systems. The most significant energy consumer is the swimming pool, and I will show you the pictures from there. So this is the marina, how it looks like. So pretty much more than half, more than 60% of the boats there are for renting purposes. This is the location of the intake well. So in the corner of the marina, next to the swimming pool, it is the intake well, and the pipe that is returning the seawater system is behind the second boat that is on the picture left. So this is how it looks inside of the engineering rooms, very similar to what has been shown on the previous presentation, the compressing units, the heat exchanger network, and this is the monitoring PLC, where I've taken a picture that everyone can see that for this particular seawater heat pump system, the intake temperature was 19.4 degrees Celsius. Still, it has to be, it is heated up for the hot water system needed for the hygiene inside of the swimming pool to 56 degrees Celsius. And it is its COP is 3.48. The temperature that is providing to the two pools inside of the building is, for the bigger pool, is 28.5 degrees Celsius, and for the smaller one is 28 degrees Celsius. And I will stop here. I want it to be very short because we are now right on the time for the Q&A sessions, for the open discussion. I hope that everyone that was following us online is satisfied with the presentation during today's lab, Blue Deal Lab. We heard the presentations from our speakers. It was Professor Krajic that Croatia has a local sustainable action plans and acts for smart islands development and optimization tools for smart islands planning and are gaining on momentum, but in the end it is up to the local population. So I will just briefly summarize what has been said today. From Matteo and Morena, we heard that currently various designs of technologies are available for wave energy and offshore wind turbines. Even more is required to develop floating structures. Wave farms can come in cage arrays coupled with offshore infrastructure or even PV panels for floating renewable farms, hybrid blue energy platforms. From Frederica, it was a comprehensive approach that takes into account biodiversity, navigation, and bathymetry using the GIS tools. Methodology is developed in a way that intersects about the previously mentioned parameters and excluding the areas that are not in scope of it. Acquisition of the geodata is the most challenging task, while Posidonia and navigation routes are the most limiting factors. As for the presentation from my colleague Hrvoje Stanchin, we showed that it is possible to have a significant amount of the electricity production from offshore wind parks that were selected in the Split Dalmatia County, and we can conclude here that Split Dalmatia County can be the pioneer in the Croatian energy transition. As for, sorry, I forgot for Kostas, the information, engagement, debate are the main objectives for visualizations in the planning processes and visual impact assessment. Limitations are mainly the availability of data for technologies or landscape and partially software capacities. Sorry. Ricardo was saying that emission factor are less for offshore, so CO2 emission factors are less for offshore wind farms, which is reasonable because less fossil fuels are used. Then for the CO2 emissions from the current Croatian electricity and energy system. From Boris, we heard about the study visits for the seawater heat pump systems. These technologies can be used for heating and cooling for various purposes: cultural heritage, hospitals, hotels, households. Modular design allows installation of various nominal capacities. So for different types of buildings and different use. Introduction of seawater heat pump system association might help in promotion of this technology and greater development. I hope that I summarized in brief today's presentation. I will now open the floor for the questions to our presenters. So to people that are physically here and which are online. So I'm waiting. Any questions? Okay, Felipe. Yeah, microphone. Please introduce yourself and refer your question to the presenter.
My name is Felipe Feijóo from University of Zagreb. So I have two questions. One quick question for Ricardo Pulselli. Just a clarification. I didn't fully get if the forest land that you were saying was additional forest land, basically forestation, or is existing forest land to capture basically the additional CO2 emissions. And second question for Herboya. And maybe it's not only for you, but in general. So when you show the economic analysis, basically to recover the investment, you assume a fixed price or an average price of 55. But I think in general, when you have more renewables, the electricity price will likely go down. So the average price is maybe an optimistic case, especially in the future. So thinking in general where renewables will be more deployed, how can we actually create policies that will incentivize the deployment of more renewable energy? So those are my two questions.
Okay, Ricardo, may you first answer the question regarding the surface of the forest area?
Yes. Well, the forest land is just a virtual forest that we used to visualize the impact in terms of carbon emissions of the electricity sector. The electricity production in Croatia provide 8,000 kilotons of equivalent carbon dioxide. To absorb that quantity of carbon dioxide, you need a forest of 12,000 square kilometers. The current absorption at the national level in Croatia is 5,000 kilotons of carbon dioxide. That is much less of the energy emission, the emission of the energy sector. So it is not enough to compensate the current emissions of the energy sector, and you have also to consider that the impact is even more. The energy sector is not the full picture, but there are other sectors missing in this balance. So it's not enough. The forest land was just a visualization of the impact, and it is an intensive forest. So in some cases, it's even the forest land in Croatia is even less intense in terms of carbon absorption than that I represented in that picture. But anyhow, it's just a comparison of numbers.
Okay, thank you, Ricardo.
Yeah, thank you for your question. Regarding the electricity price that we assumed here in this study, 55 euros per megawatt was just to show what would it be on annual basis. But also I took the data for 2019 because for the 2020, this average price was 10 or 12 euros lower. So yeah, this really varies. And if you go to intraday trading, you can see the prices go from, I don't know, for example, from 55 to 60, 70, 80. But since this was not part of this analysis, because this is more focused on energy markets and how to optimize this thing, we use this price just to show what would it be in general, in which period can you expect the return of investment. And also is the similar for this investment cost because they greatly vary. For example, if you go to the bathymetry that we considered for our site, most probably the cost would be even higher than we assumed in this estimation. So this was just to show in general what would be the return of investment, but to go more in-depth analysis of this requires more sophisticated approach.
Okay. Stay on with the microphone. The next question is again to you, Hrvoje. So it is from Professor Kajic. It is 1 terawatt hour of natural gas in transport. Can you explain that number?
Yeah, because probably there is some public bus transportation that is using natural gas, is compressed natural gas. Also, there is some demand for the private cars. And finally, maybe to get better clarification, we should ask the Hrvoje Požar, which made this report where this data was taken from.
Okay. Do we have some more online questions? If not, can I start with Mike? Oh, okay, we have first.
So I have a question for.
Please introduce yourself.
I'm sorry. I'm Vladimir Vidovic from Zdeve Center, and I have a question for Ms. Federica. Do you have any capacity factors for wave energy converters that would be installed in Croatia, specifically in Dalmatia? And I have a second question again for Hrvoje. You mentioned the wind turbines of 6 megawatt capacity. Could we consider bigger wind turbines like now there are wind turbines that are testing with 12 megawatts capacity?
Yes, Federica, we are listening.
Well, for your question, no. Actually, no, we do not have. We have not considered this. It's presumably the next step to take into consideration when going into more in-depth analysis for the wave energy converters.
Thank you.
Yeah, maybe I can just add something to Federica's answer. For preliminary assessment that we carried out for some other sites, not on this site here for Split Dalmatia County, the load factor was between 5 to 10%. So it's really, really low. And also a question for me was, the size of the nominal capacity of wind turbines. We considered 6 megawatt because you have to take into account that this is the offshore floating structures that need to carry out this. So 12 megawatt is not problem for onshore maybe, but for the offshore, especially floating offshore, might be at least at this stage of development. But of course, this could go greater and it would be even better when the sizes are bigger, of course.
I would just like to add another question. In case with bigger capacity, should we consider bigger distancing between the wind turbines on the field?
This is derived from the size of the geometry of the turbine.
Okay, any other question from online participants? No? Okay, there is one question in the public here.
Okay, just to continue with Zdeve Center staff. Hi, my name is Nikola Matak from Zdeve Center. My question is for Mr. Riccardo Pulselli. You were mentioning some CO2 emission factors for Croatia and also the emissions from electricity production, and the numbers you mentioned are not the ones that I look in like official statistics. So I'm just wondering, where did you get the data? Just so we can compare and see it.
Oh yes, there are always different sources for this information, so sometimes there can be some difference. The basic reference for me was this National Inventory for Greenhouse Gas Emissions 2020 of Croatia. And also we took the emission factor for the electricity grid mix from a source we shared with Unizagreb. I don't know exactly, but it looks coherent with the share of renewable energy sources and thermal power plants that we have found in terms of absolute values. Probably one factor that can contribute to change this number is the high percentage of net imported electricity, because in some cases the emission factor of that portion is can change from case to case.
Okay, I have questions, if I may now. I have questions for geoimaging. So it is related to the visualization of the offshore wind farms. So just tell me, is it correct? So we were looking from the elevation of 500 meters. And also we were looking from the coastal area. So what would be the visualization, how it will be seen from the beach. So since this, and we also saw it, that public acceptance, it's a major concern because this is a tourist region. My question was this visualization for, let's say, a perfect day, a clear day, where you have clear visualization, or it can be also, so it's a difference when it's a sunny, clear day after the rain, and when it's you have the during the summer evaporation from the water. So it's not that the visibility is not that high. Sometimes it can be the horizon can be for 20 kilometers. Sometimes it can be less. So please.
Yes, absolutely. That was one of the biggest challenges, since we are aware that in the North Sea, for example, it's much easier to visualize the horizon and place the wind turbines there and conduct a more systematic analysis when it comes to the VIA, the visual impact analysis. However, in the Mediterranean, there are the landscape is much more complex, and you have to accommodate the anxieties and the needs and the requirements of much more stakeholders involved. Tourism is one of this, for example. In our analysis, what we try to do is try to replicate a hypothetical scenario where some of those requirements are met. And you are right to pinpoint that the elevation of the eyesight of the camera is important. In the tool, you might see that there are different ways to look. There are different angles from different islands. 3 of the viewpoints are taken from average height, from up to 2 to 3 meter eyesight. So it's on the beach level. There are some nice viewpoints from the surrounding hills. I know that in the island there is an elevation of 230 to 280 meters. So we try to place the camera there. And indeed, what you get as a result is with clear weather conditions. So we try to shift it towards the worst case scenario. What a person could, it's not the worst case, but it's the scenario that with a really clear visibility, a very clear atmosphere, in order to provide the visual dimension under circumstances that this creates the biggest effect. So this is how we try to do it, and of course it's natural to think that structures that are up to 100 and 170 meters with a rotor blade, they could be visible. They could be visible for from quite a distance, especially with the technology progresses and the visual impact increases. However, as Ricardo also pointed out, Mediterranean is full of structures that may look abandoned. I don't know what looks better. Is it an abandoned block of hotels in the Costa del Sol, or an abandoned oil rig? Is it better than a wind turbine? We really should start a discussion to think about it.
Okay, thank you for your answer. I have a question for Federica. So, what would be the needed data for further improvements of your analysis?
Well, this is a really key question. Of course, it depends basically what is the objective of the analysis. That is, for example, if we focus on wind turbines, of course, there will be the necessity of getting very detailed data, for example, on birds' migration routes and on birds' paths, because it is crucial to assess the impact of the turbines on the birds. Another thing that would be good to understand, for example, is as also Kostas highlighted, is how the seabed looks like. And this is very important to understand, for example, to choose the most appropriate mooring system and to assess its prospective impacts on the seabed. Of course, it depends on the level of detail you want to achieve, and so what the purpose of the analysis is. If it is for a real situation when you have to install a specific device and a specific technology, then the level of detail is much more high. It's much higher. For example, there could be the need to measure the specific characteristics of wind speed in that specific area, and so perhaps the local level monitoring will be needed. Also for the wave energy, the issues are mostly the same. So it depends. Of course, the more you have to, the more you want to go forward in the planning and in the design of the plant, the more you will need to make very specific monitoring. Of course, also other data that we tried to incorporate would be perhaps also related to specific site-specific regulations regarding the use of the marine space, and this would be for sure an issue of the maritime spatial planning.
Okay, thank you very much for your elaboration. We have time for two more short questions. I would like to put one in front first to Morena and Matteo. So, what is the technology readiness level for the hybrid systems, the blue energy systems? Are there developments in this way, or is it just on pilot installation? So, what is the progress?
Okay, basically they are a line of research, so they are in terms of pilot project. In this case, the technology readiness level is low, but it could be an opportunity for the development of this kind of technologies in the blue energy sector.
Okay, my question is related to tomorrow's video, so you will see what the students from Zagreb proposed as a solution for one open innovation challenge. I hope that you will be able to follow it tomorrow. So
Okay.
another question is coming from the audience here. So the last question, so colleague of mine.
Yeah, I'm Hrvoje. I have a question for Mr. Ćosić. Since now you gathered experience in deployment of seawater heat pumps, what would you emphasize that is the biggest problem and the biggest drawback for greater deployment of such installations?
Thank you, Hrvoje, for the question. So, from my experience, we had the biggest problem with total cost of the investment. It's changed very much what we planned and installed completely. So it's doubled in the 1 year period. So that was one of the biggest problem. Because the cost of the investment and cost of the work is changing on a 6-month basis and is increasing very, very fast. Regarding the legislation and the process of obtaining the different license, actually we didn't have problems, but we only had the problem to find out who is responsible for that. So that's the biggest problem. So you need to see who is responsible for the installation or issuing license for your plant. So is it importance of the government or on the county level or on the municipality level? So you need to find out who is responsible for your pilot, for your installation of the pilots. So that was the problem in our case. Luckily, we didn't have. I cannot say for all other projects in this field, because in the case of Dubrovnik we had the old installation, and this was the replacement, and we didn't need to get all the license. And in the case of the Crikvenica, we already had installation of the well on the sea, and we didn't have any construction work on the sea. And then if you have the construction work, then you can have the problem, because you need to request the license from the city, and you cannot have the construction work during the summer, so you need to plan an installation of your pilot in this period. So these are the problems occurred in the case of our pilots. In the Greece, they actually obtained the license in 1 or 2 weeks for drilling. So they have drilling, and this is the completely different to our case studies. So more or less everything existing, but as I said, cost, one of the problem. You need to see to find out who is responsible for license. And there is a problem of the planning, because in the summer period you cannot have the work on your wells and on the coast. So you need to plan very, very careful in the case of the installation pilots. So.
Okay, thank you for your questions and answers. We are half an hour behind our schedule, so I thank all of the presenters, all of the listeners online and physically here for making this second day successful. I hope that you have been enjoying it, and we will continue tomorrow in the same time at 10 o'clock. So stay safe and be good until tomorrow. Thank you. Bye to everybody.
Thank you. Goodbye.
Goodbye.
Bye. Goodbye.
Bye.